Hey everybody, in this video we are going to be going over spontaneity, and we will go over one free response question straight from the AP exam and some multiple choice questions from the Chemistry Olympiad, and this will allow us to become masters of spontaneity. Sounds awesome, right? Well, without further ado, let's begin. And note that some of these questions will involve topics from previous units, especially topics about equilibrium, which is Unit 10. And of course, you are expected to be carrying knowledge from previous units as well. So I expect a lot from you, and let's get started then. So we have this table right here. We have reaction XYZ. We have the equations for these reactions written in double arrows, so they seem to be in equilibrium according to the reactions. And let's take a look at the delta H, delta S, and delta G at 298 Kelvin. I think that's in Kelvin, right? Yep. So these reactions aren't actually at equilibrium. They just draw double arrows to show that these reactions can go forwards or backwards. But since the delta G is positive, it should be non-spontaneous, but they write a double arrow still. How weird. Well, we're not going to think about that. Instead, we are going to focus on what the problem gives us. And yeah, so answer the following questions using the information related to reactions XYZ in the table above. So let's take a look at A. For reaction X, write the expression for the equilibrium constant Kp. Well, let's look at what reaction X is. It's that. Now, we always include, I think, three things, actually two things in our Ks. So, in our Ks, we always include aqueous substances and gaseous substances. We never include liquids or solids. But this is Kp. Kp is for pressure. So, we will only include gases. And look at that, we conveniently have three gases over here, which is great. So, since that's perfect, let's write the equilibrium constant, or the equilibrium expression, for the constant. So, products over reactants, look at the coefficients. It's going to start off as the pressure of carbon monoxide gas, the pressure of H2 gas, all over the reactants. We ignore carbon solid, and we look at just H2O water, which is in its gaseous form, so it's water vapor. So the pressure of water in its gaseous form. So that's our Kp expression, not too bad, and we don't have any exponents because they're all 1, because everything in the reaction has coefficients of 1. So that was a pretty easy problem. Let's move on. B. For reaction X, will the equilibrium constant Kp increase, decrease, or remain the same if the temperature rises or increases above 298 Kelvin? Justify your answer. So we know from Unit 10, from a special formula that we learned, that an increase in temperature for an endothermic reaction, and we know it's endothermic because reaction X has a positive delta H. We know that increasing temperature for an endothermic reaction will increase K. But let's use the things we learned this unit to prove why, and that's how we will justify our answer. We know that delta G naught is equal to negative RT ln K. But we also know that delta G is equal to delta H minus T delta S. So substitute that in, delta H naught minus T delta S naught. Now let's move things around using algebra, and we're going to kind of isolate K to see how T influences K. Divide both sides by negative RT. We will get, let's see, delta H naught over negative RT minus T delta S naught over negative RT is equal to the natural log of K. Now, the T's cancel out. A negative times a negative is going to be, well, actually in this case, it's actually a negative divided by a negative, but same thing, it becomes a positive. And let's see, yeah, that stays the same. So in the end, we get, let's move the positive term to the front. So delta S naught over R, which is positive, minus delta H naught over RT is equal to the natural log of K. And rearranging this, we know that e to the delta S naught over R minus delta H naught over RT is equal to K. So you are going to be using this equation to prove why increasing the temperature will increase the K. Here's why. We know that delta H is positive, so this entire term will be positive. By increasing temperature, the denominator increases, which causes this value, this term, to decrease. So we're subtracting by a smaller number. Now we subtract a smaller number, the exponent will get bigger. So bigger. Because if you subtract a smaller delta H naught over RT, you are going to get an exponent that's going to be bigger since you're subtracting less. And e to a bigger number, well, e to a bigger number is a bigger K. So we just proved that an increase in temperature leads to a bigger K using this equation. So what you would write is you would kind of derive this equation to justify your answer, and you would say, according to this equation, so let me kind of scroll down, according to this equation, an increase in T given a positive delta H naught will result in an increase, in this case it's in Kp. There you go. You don't have to explain how smaller, bigger, bigger. They get the point. You just have to make sure to connect the equation to the fact that an increasing temperature will increase the K. Let's take a look at C now. For reaction Y at 298 Kelvin, is the value of Kp greater than 1, less than 1, or equal to 1? Justify your answer. Well, we know that delta G naught is equal to negative RT ln K. And you can kind of see where things are going. We just need to find K. Well, we don't even have to find it. We just need to see if it's greater than, less than, or equal to 1. So, as we can see, the delta G naught is positive 91. Alright, so if it's positive 91, let's write that here. Well, actually, no. Sorry, that's the wrong one. We looked at the wrong equation. We're looking at reaction Y. Well, reaction Y is also a positive value, positive 29 kilojoules per mole of reaction. So 29 kilojoules per mole of reaction, we won't write that, is equal to negative RT ln K. Now, you have to think about this in terms of math. So it's a little bit hard, but we can do this. So this is initially negative, and the only way for this term to be positive in order to get, this term to be positive is if ln K is negative. So how is ln K negative? Well, we know that the natural log of 1 is 0. So if K was 1, it would be 0. But we don't want that. We want a positive value. So actually, no, we want a negative value for natural log of K in order to get this entire term to be positive, just like the 29. So if we take something less than 1, like the natural log of, I don't know, e to the negative 1, which is less than 1, you will get negative 1. So look at that. If this term in here, if K is less than 1, we will get a negative value. So that's what we need. So I guess K has to be less than 1 for this system to be true and for this term to be positive to match, the 29. But, of course, I'm not very satisfied with proving it that way. I kind of want to know the actual answer. But this would be the fast way. The slow way would be to solve it. 29 is equal to negative 8.31 times 10 to the negative 3. This is kilojoules per Kelvin. This is in kilojoules. Note how the kilojoules match in units. And our temperature is 298. And this is times the natural log of K. let's divide 29 by all this. So 29 divided by negative 8.31 times 10 to the negative 3 times 298. So we're dividing all that. And I got negative 11.71 is equal to the natural log of k. And I'm going to ignore sig figs here because they don't want to know the exact value. They just want to know it's greater than, less than, or equal to 1. And that's what we're trying to do, so let's go ahead and do that. So e to the negative 11.71 is equal to k. And let's see, what's e to this? Oh, wait, e to the negative 11.71, I got 8.21 times 10 to the negative 6 is equal to k, and that's less than 1. So, two ways to do it. I like the first way. If you like to solve it directly, that's on you. So now, let's do D. So let me erase all this work. Erase, erase. And what does D say? Oops, I don't want to erase all that work because some of that's actually the question that we need to answer. So let's take a look at D. D says, for reaction Y at 298 Kelvin, which is larger, the total bond energy of the reactants or the total bond energy of the products? Explain. So this is going back to Unit 6. Note that how we're going back into the past, but that's fine because we can do this. So we know that bond energy is related to delta H. So the delta H for reaction Y is actually positive 41 kilojoules per mole of reaction. Now, does this mean that the bond energy of the reactants is greater than or less than the bond energy of the products? Now, we have to think about this. We know that the delta H is equal to the bond energy, well, let's think about this. The bond energy of the reactants. So remember, when we are looking at reactants, we're looking to break the bonds. If you break bonds, that takes energy. So it's going to absorb energy, so this is going to be the positive value. Now, when you form bonds, or when you form the products, you're going to be making some bonds. And let's see, bond energy of products. And the reason why we're subtracting is because the bond energy of the products, you are forming them. If you form bonds, you are releasing energy. So this entire value over here should be negative because you are releasing energy when you form bonds. So it's an exothermic process when you form bonds. So that's why there's a negative sign there. So if we think about this, if this delta H is positive, does this have to be greater than this? Well, yeah. If this is greater than this, then if you subtract them, you kind of get a positive number. So you can say that the bond energy of the reactants will be greater. So let's say bond energy of reactants is greater than the bond energy of the products. Now, how do you exactly explain this? Well, you can say that the energy it takes to break the bonds, which is an endothermic process, is greater than the energy released by forming the bonds in the products. Therefore, overall, more energy is absorbed than released. So the net change in energy is that more energy is absorbed, which is why we have a positive delta H. So just convert what I said into words, and that should be the explanation. Now let's take a look at E. Is the following statement true or false? Justify your answer. On the basis of the data in the table, it can be predicted that the reaction Y will occur more rapidly than reaction X will occur. So let's take a look at what's going on. So Y and X. So it's saying that Y will occur more rapidly than X will occur. Is that true though? Well, we can see that Y has a smaller delta G than X, which means that this process will pretty much be less spontaneous at the same temperature. So this K will be larger because of the smaller delta G, and because this delta G is more positive, it's less spontaneous, so the K will be a little bit smaller. So this is all at constant temperature, by the way, and based on this logic, we can't say that one will go faster than the other, because that's not what K gives us. Just because the delta G is bigger does not necessarily mean that it will go slower. Remember, spontaneity and reaction rates are two different things. So just because the K is bigger doesn't mean that it'll go faster. In fact, it could go really slow. Who knows? So this is actually false because equilibrium constants do not determine the rate of the reaction. So one cannot conclude the relative rates based on the table. And you can also add that the equilibrium constants come from the delta G naught values. So this would be my explanation, and yeah, so this is false, and let's write false all the way because you want to make yourself clear. Now let's do 1F I. Consider reaction Z at 298 Kelvin. Is delta S positive, negative, or 0? Let's look at reaction Z. Is the delta S positive, negative, or 0? Now, there's 1 mole of gas, there's 2 moles of gas, there's 1 mole of solid. And we can say this has a value of 100, a 1, and a 200. 101 minus 200 is negative 99. And this tells you that it has a negative delta S. But you can also think of it this way. 2 moles of gas is becoming 1 mole of gas, which has less entropy overall than 2 moles of gas. So there's a decrease in entropy, and no one cares about the 1 mole of solid, since the entropy of that is non-existent compared to the entropy of the gas. And that's not true because the entropy of carbon is large, but it's significantly smaller than the entropy of carbon dioxide. So I was just exaggerating, but this should have a negative delta S. Negative because we can say that the system, or the reaction produces less moles of gas, leading to a decrease in entropy. And you can also add that the production of carbon solid does not matter since the entropy of carbon solid is significantly smaller than the entropy of a gas. There you go. Determine the value of delta H for the reaction. That's a little tricky. How do we do that? Well, we have to actually think about what's going on. We don't have any delta S or delta G values to calculate delta H. So how do we calculate delta H? Well, we do have the delta H for these two. Maybe you could do Hess's law, since this reaction looks similar to these two reactions. Maybe we could do something there. So let's actually copy the reactions to the right side, and let's solve for, I think this is 1F2. So the first reaction is carbon solid plus H2O gas becomes, I'm not going to write the double arrow, kind of confusing, CO and H2. So let's write that. CO plus H2. And the delta H naught is, let's see, 131. kilojoules per mole of reaction. Let's copy the second one. I'm going to try to memorize this and get it in one go. CO2H2, COH2O. Alright, let's try to memorize this. CO2 gas plus, I forgot it. Let's try this. CO2, H2CO. Okay, H2 gas becomes CO, and I'm pretty sure that was H2O. And the delta H naught of this reaction, so let's just label that as 1 and 2, is 41 kilojoules per mole of reaction. Now, what do we exactly need? We need 2 COs on the left side, and we need a C and CO2 on the right side. So right now, all our COs are on the left side. Why not flip both of these reactions over so that we can get COs on the left side, which is what we want for reaction Z in order to find the delta H for reaction Z. So let's do some flipping. So H2 gas plus CO gas becomes C solid plus H2O gas. The delta H naught of 1, well, we flip the reactions, I'll call it -1. It's -131 kilojoules per mole of reaction. And we have to flip the second one as well. And usually when you do this, things turn out right, and that's what we want. So this is H2O gas becomes H2 gas plus CO2 gas. Delta H of -2 naught is -41 kilojoules per mole of reaction. So we're going all the way back to Unit 6. And what do we want? We want 2 COs on the left-hand side and 1 C and 1 CO2 on the right-hand side. So I think it's time to add these two, since we have 2 COs on the left-hand side. I see the H2Os canceling out. I see the H2s canceling out. And what do you know? We're left with 2 CO gas on the left-hand side becoming carbon solid plus CO2 gas. And hey, that matches the equation at the bottom. And that's what usually happens. It usually works out in the end. And we will add these two values. -131 minus 41 is actually just -172 kilojoules per mole of reaction. And we followed sig figs all the way through, so good job, guys. One last problem. We can do this. We are so close. A sealed glass reaction vessel contains only carbon monoxide gas. So let's just draw a glass vessel for some visualization. And a small amount of carbon. Okay. So let's call that carbon. If a reaction occurs and the temperature is held constant to 298 Kelvin, will the pressure in the reaction vessel increase, decrease, or remain the same over time? Well, I don't know. Let's figure this out. This is going to be the reaction between CO and C. Do we have anything for that? CO and C. Well, I see this reaction over here. This reaction seems to have only COs and Cs, and I have a feeling that the COs might convert to CO2s. Quite an interesting system. So I think this is going to be based on reaction Z. Oh, wait, I didn't even read that. This is based on reaction Z, so we have to use reaction Z to help us out. So 2 COs, let's write that out. 2 CO gas becomes, I forgot, I think it's just C and CO2, all right? C solid plus CO2 gas. So it's saying the reaction occurs. So this reaction is happening. Will the pressure decrease, increase, or remain the same? Well, we're actually decreasing the amount of gas because we're going from 2 moles of gas to 1 mole of gas. And the change in the moles of gas, let's write moles of gas as Ng, is -1 moles per mole of reaction in this equation. And, well, if we're producing less gas over time, the container will have less gas over time because the net change in the moles of gas is -1 moles of gas per mole of reaction. So the amount of gas in the container is decreasing over time. So because delta Ng is negative. So we can kind of prove this by saying that 1 minus 2 equals negative 1 moles of gas per mole of reaction. Then the reaction will decrease in the moles of gas over time. This leads to less moles of gas. And because PV equals nRT, we're doing gas laws because this is pressure in moles, and for a constant V and T, because they said they kept T constant, then a decrease in the moles of gas will lead to it's a decrease in pressure, since, and you don't have to write this, but I'm going to write this, since moles of gas is proportional to pressure according to this equation, since they are on opposite sides, and we can see that a decrease in moles will lead to a direct decrease in pressure. So that's what it means for N to be proportional to P. So there you go. That's how you do that free response. It was kind of tough, but we did it. So nice job, everybody. Now let's actually move on to the questions that I am interested in talking about, which are the multiple choice questions. So let's get ahead and do that. Let's do some multiple choice questions now. Upon which factors can the Gibbs free energy change for a reaction depend? So this question is saying, what factors does the Gibbs free energy depend on? Does it depend on temperature, or the concentration of species in solution, or maybe both? Well, we know that delta G is equal to delta G naught plus RT ln Q. Now, remember, Q represents basically the reaction quotient, and this tells us the ratio between products over reactants. So obviously, if we change the concentrations of species in the solution, this Q will change, so delta G will respond to that. So delta G definitely depends on the concentration of things. Now, what about temperature? Well, yeah, it's part of the equation. Increasing or decreasing this will absolutely affect the value of delta G according to the equation. So our answer for this one is actually both 1 and 2. So the answer is C. Now let's take a look at this. Which has the greatest entropy at 0 degrees Celsius? So we're going to cross out A and B immediately, because we know that gases always, well, almost always, have the most entropy. Now what about this? That's a little bit interesting, actually. This is 1 mole of gas. This is 1.5 moles of gas. Which one do you think has the higher entropy? Well, more moles of gas equals more entropy, because if we convert these to arbitrary values, as we did for the very first video of this unit, this would be 100, this would be 150. So it's very safe to assume that the answer is D. And in fact, it is. Let's take a look at this problem. What is delta G naught, a formation of CH4 at 298 Kelvin? Okay, so our goal is to find this missing value right here. How can we find that missing value? Well, we can use the summation formula that we know. The delta G of reaction is equal to basically the sum of the products of the delta G of formation for the, well, I don't need to write the products because I already wrote that, minus the reactants, and this is the delta G of formation. And we have to consider the amount of moles there too. Moles matter. Alright, so moles matter. But we have some things missing. We do have, let's see, we do have all this stuff except for, of course, the delta GF of the CH4. But we don't have the delta G of the reaction. But wait a second, what is the reaction? Now, what is the reaction? Well, let's think about this. Can we somehow form a reaction from these four substances? Well, of course. Why not, right? So, why don't we combine some chemicals to see if it works? So, obviously, we want C, H, and O on both sides. So, let's keep a note of that. So, I think what I want to do is I want to combine CH4 and CO2 gas. What might happen? Who knows? But the question is, can we balance this equation? We'll find out. And if we can't, then we'll resort to a new equation, and maybe it will make a lot more sense. So this would be H2O gas. Uh-oh, I see a problem with this, because there's C's on this side, and there's no C's on this side. Bad equation. So we're going to erase this equation and find a better equation to write out. So I think we need these two, well actually these two to be on the left side this time. CH4 gas plus H2O gas becomes H2 gas plus CO2 gas. So let's try to balance this out. We have one carbon on both sides. We have actually 6 hydrogens on this side and 2 hydrogens here. So let's put a 3 there to balance that out. And we have actually 2 O's here and 1 O here. Let's put a 2 there. But by putting a 2 there, we now have 8 hydrogens. So we need to put a 4 here now. Is everything balanced? Well, let's find out. Let's see. So 1 carbon here, 1 carbon here, 2 oxygens here, and 2 oxygens here, and 8 hydrogens here, and 8 hydrogens here. Voila, we have a balanced equation. And when we have a reaction, even though this might not even be a legit reaction, we still have a reaction, and this will help us solve the problem, because it gets us a reaction to work with, and that's what we need. So, let's see. Let's find the delta H of this reaction, since we have all the delta H formations, the heat of formations. So, let's get out our handy-dandy calculator to calculate the delta H of this reaction, and it's going to be naught. So, our product is 1 CO2, so negative 393.5, and that's going to be added with 4 times the delta H of F of H2. Oh, it's 0. What do you know? And that's actually a very important point because the delta H and the delta G of formation for H2 will always be 0, as I discussed in video 11.3. So that's great. This cancels out, and we're going to subtract by the heat of formations of the reactants. So we have 1 CH4. The heat of formation of CH4 at standard state is negative 74.8. And 2 H2O, so we're going to be adding 2 times. Now, what's the delta H of formation for H2O? Well, it's negative 241.8. And what do you know? We got the delta H from that. We just have to type in our calculators. Negative 393.5 minus negative 74.8 plus 2 times negative 241.8. And this gives us a delta H naught of 164.9 kilojoules per mole of reaction. Now, here's where I want you to be careful. This is joules, not kilojoules. So why don't we convert everything to kilojoules by multiplying everything by 10 to the negative 3? Because by multiplying joules by 10 to the negative 3, you get kilojoules. Like 1,000 joules becomes 1 kilojoule when you multiply by 10 to the negative 3. So we essentially want to do the same thing for the delta S naught reaction by taking the entropies of the products minus the entropies of the reactants. It's all summation. So How do we do that? Well, we take the reaction again, and we know that the entropy of CO2 is, let's see, 213.7 times 10 to the negative 3. 213.7 times 10 to the negative 3. And this is going to be added to the entropy of 4 H2s. So that's H2. So it's going to be 4 times 130.7 times 10 to the negative 3. And we are going to be subtracting by the entropies of the reactants. CH4 is 186.3 times 10 to the negative 3 plus, let's see, we have two H2Os, so two of these, so 2 times 188.8 times 10 to the negative 3 to convert to kilojoules. And typing this into our calculator, we get, let's see, so I'm typing this in, and it's taking a while, as expected, because there are a lot of numbers to crunch together. So I need to make sure that everything is typed correctly. 188.8. And I got a pretty interesting answer. I got a delta S of, well, let's not write the delta S because it's in the front. It's going to be 0.1726 kilojoules per mole of reaction, and of course we can't forget the K. So we can now find the delta G of the reaction. Delta G naught of reaction is equal to delta H naught of reaction minus T delta S naught of reaction, and all we do is plug and chug to get delta G. So let's go ahead and do that. Let's see, delta H will be 164.9 minus T, I think it's at 298. There you go. 298 times 0.1726. And this should get us, let me type this into my calculator. This gets us a delta G naught of 113.4. Well, let's do 5 actually, because I have to round up. So, obviously, this reaction doesn't actually work. It's kind of non-spontaneous because of the positive delta G value. That's fine. Now let's use this summation. So we have the delta G of reaction, 113.5, is equal to the delta G of formations of the products. So we know what our products are, H2 and CO2. So let's see. We know that the delta G formation of CO2 is going to be negative 394.4. So let's do that. Negative 394.4. And we know that the delta G of formation for H2 is going to be, well, 0. So we can ignore that because it won't do anything. And we subtract by the sum of the delta GFs of our reactants. So we have our CH4, so let's call that X. The delta G of F for the CH4 will be X. And we have two H2Os, so it's going to be plus 2 times the delta GF for H2O, which turns out to be negative 228.6. Negative 228.6. Now, let's solve for X. So I'm going to do this algebra, plus 394.4. I'm going to add 394.4 to both sides, and I'm going to do some algebra. 507.87 is equal to negative. So let's actually distribute this negative twice. So it's going to be negative x, and negative times a negative is positive. So what's 2 times 228.6? Well, it's just 457.2. Now let's flip things around. X on the right side, on the left side by adding x to both sides. And let's subtract this number from both sides. and 457.2 minus 507.87. And note that I'm not really too worried about sig figs here, but of course we could worry about sig figs if we wanted to, so let's just call that 9. Let's call this 0.9, and I will get x is equal to 50 negative 50.7 kilojoules per mole of reaction. Is that an answer choice? I hope so. Negative 50.7, voila. It is A. So we did a great job. That was a ton of work, but we applied knowledge from basically 3 different chapters or units, and we did it. Let's move on to the next problem. Let's take a look at this problem. A reaction takes place by an uncatalyzed pathway, whose reaction coordinate diagram is shown below. Alright, so this is called a reaction coordinate diagram, and let's take a look at this. So this point up here is going to be the initial, our reactants. This point right here is going to be our products. And we should note that this delta G over here is going to be, let's see, that's going to be a negative delta G value, or a delta G value that is less than 0. The reaction is accelerated by addition of a small amount of catalyst, which reaction coordinate diagram, drawn to the same scale as the one above, best describes the catalyzed reaction. So let's take a look at these. So we know that when you add a catalyst, the K doesn't change. Only the rate changes. Both the forward and the backward speed up at the same rate. So that means the K is going to be the same. So what does this mean? Well, this means that the K won't change, and because delta G naught is equal to negative RT ln K, if K stays constant, then you can be sure that our delta G stays constant. And that means that in this reaction coordinate diagram, the delta G will stay the same. So adding catalyst will not change the delta G. That was the point. So we have to cross out the answers where the delta G changes. So it looks like for all of these, the delta G is actually, it goes from higher to lower. So all of these have a negative delta G, which is great. Now let's figure out what it means to add a catalyst. When you add a catalyst, you're lowering the activation energy. So what I'm looking for is for the activation energy, EA, to become smaller. So if I see the peak go up, that's not a good sign. A just looks like that diagram we just looked at. Now let's take a look at B. B has a higher peak. That's an increase in activation energy. That's not what we want. That actually slows down the reaction and does not speed it up. This is what an inhibitor would do. But we want a catalyst, not an inhibitor. Now these two reactions are quite interesting. We see the peaks decrease, but there's more than one step now. We're in a bit of trouble. And both of these peaks decrease. But they're so similar. Which one do we choose? Well, what's with this down there? It seems like an intermediate is more stable than the products. And when we learn about intermediates, we learn that intermediates are intermediates because they are technically unstable. But it seems like this intermediate is super stable because it has low energy. Low energy equals stability. It seems like this intermediate is more stable than the product. So if you think about it, why would an intermediate who's more stable than the product want to become a product if it's happy where it is? So this reaction coordinate diagram makes no sense, which is why the answer is C. Let's take a look at the next question. Now this one is interesting. The solubility of lithium carbonate in water at 298 Kelvin is 0.175 moles per liter, and its solubility decreases with increasing temperature. Okay, so as we increase temperature, our solubility goes down. Now, that actually means that our KSP goes down. This is Unit 10, where we learned about K. And we learned that as K becomes smaller, the solubility decreases because K is the product of the concentrations of the ions, and the KSP decreases, then the product has to be smaller, which means that each of the individual concentrations has to be smaller, which means that less dissolves. We'll take a look at that a little later. What are the signs of delta H and delta S for the dissolution of lithium carbonate? Now, we just learned this special equation. Let's actually reprove it to ourselves. We know that delta G naught is equal to negative RT ln K. We know that this can be substituted for delta H naught minus T delta S naught. And I'm going to save my voice and let you watch the algebra go along because I've already done this. So I just did a bunch of algebra, and if you want some algebra practice, you could follow along. But if you don't, well, you could just watch me. So this is a special equation that relates basically everything to K. So we said up here that according to the problem, an increase in temperature decreases solubility, but I claim that it also decreases KSP. Well, that's because the KSP for this reaction over here is just the lithium concentration squared times the carbonate concentration. And if you think about it, if things are less soluble, these two must be decreasing since less ions are dissolved when solubility decreases, and that causes KSP to go down. So we can see the relationship between solubility and KSP from that. Now, what does this have to do with anything? Well, before we think about this, let's just take a look at what we wrote. Increase T, decrease K. That reminds me of an exothermic reaction. And we can use this formula to kind of prove that. If this delta H is exothermic or negative, then a negative times a negative is actually going to be a positive value. Now, if you think about it, if we increase the temperature, this positive term will become smaller. So this positive term will decrease. And that means that by increasing temperature, this entire term will actually decrease in value. And because the exponent is decreasing due to this T increasing, then that decreasing exponent leads to a K that is decreasing. So, as you can see, increasing temperature leads to a decrease in K, which follows the rules of an exothermic reaction. So, we conclude that delta H naught is going to be less than 0. So, we can cross out A and B. Now, what about delta S? Well, let's take a look at this reaction over here. I mean, not a reaction, an equation. I don't know why I keep on saying that. So, we can see, well, let's just rewrite this equation to make it a little bit clearer for us. We can see that this term over here is actually going to be a positive term. All right. Now, we have to figure out whether this is positive or negative. So why not solve for K? They give us the solubility of lithium carbonate. Let's make an ice chart. I, C, and E. And of course we know it's lithium carbonate becoming, well, it's actually in equilibrium with, let me fix that table. It's in equilibrium with 2 lithium ions and 1 carbonate ion. And we have lots of this, we have none of this, and when it's established in equilibrium and dissolving, plus 2x plus x, you have 2x here and x here, and there's, well, it's actually just minus x. But you still have lots, and we don't worry about this because that's not part of the equilibrium expression. So KSP is equal to 2x, and since there's a 2 there, it's going to be squared. Well, we wrote it up here, actually, and we can see that we have to square our lithium concentration, and our carbonate concentration is just x. So we can kind of simplify this to 4x cubed. Now, we actually know what x is. X is simply the solubility, the amount that dissolved. It says it's 0.175 molar. That much of it dissolved. And look at that. That's the amount that dissolved. So they're saying that basically 0.175 molar of the lithium carbonate dissolved. So our x is going to be, well, 0.175. 4 times 0.175 cubed is going to be, let's figure this out, 4 times 0.175 cubed is going to be 0.0214. That's our K. Note that our KSP is actually less than 1. Now this is actually really important because if our K is less than 1, guess what happens? Let's take a look at this equation and think about how math works. E to the whatever is equal to K. We only care about the sign of that. So we know e to the 0 is 1. Let's draw ourselves a number line to see how this works. E to the 0 is 1. E to the negative 2 is going to be obviously less than 1. And if we type this into our calculator, we get e to the negative 2. We actually get this is actually equal to 0.135. So e to the negative 2 is going to be 0.135, or you could say that it's going to be less than 1. Now, what about e squared? Well, this is greater than 1 because e is, let's see, on my calculator it says e is actually 2.718, so it's a number bigger than 1. So e to the 2 belongs on this side of the number line, and it's going to be greater than 1. So let's actually think about this. So if this e to the whatever is equal to k, and our k is less than 1, if our k is less than 1, then we're on this side of the graph. And what is this side of the graph? Well, on this side of the graph, we notice that, well, all the exponents are negative. So this must mean that this exponent has to be negative for, the solubility to be true, for the KSP to be that. But we have a problem here. We have a positive right there. So if we want the exponent to be negative, what do we have to do? Well, we actually have to make this negative. So what can we conclude about the delta S? That delta S is negative, or else K will never be less than 1. Because if delta S was positive, if we're adding two positive numbers, this makes K super big, and our K is less than 1. So it doesn't make any sense. So this delta S has to be negative, and we don't know what value it has to be, but we just know it has to be negative, so that this exponent overall has a chance of being negative, since a negative plus a positive can potentially be a negative if the negative is large enough. So e to a negative number will yield a k that is less than 1. So there you go. We know that our delta S is negative and our delta H is negative, and the answer is D. Now this actually brings a very important point. We have to think about what our delta G is. So let me take a look at this for a second and think about this. So we know that delta G naught is equal to negative RT ln K. Notice that if K is equal to 1, delta G naught is actually equal to 0 because ln of 1 is 0. Now if K is greater than 1, then delta G will be less than 0 or negative. Now, if delta G naught is greater, well, actually, let's start with this. If K is less than 1, then the natural log of a number less than 1 will actually be negative, and negative times a negative is a positive. So delta G will consequently be greater than 0. So this could be a rule that you can memorize. That's kind of important. It's saying that things are spontaneous when the K is greater than 1, and things are not spontaneous when K is less than 1. Pretty cool, right? Should have put that in the last video. Maybe I'll put it in the description. But this is something super important that you could establish by simply, well, drawing a line graph. But you don't actually have to. So we figured that out. We have one problem to go. What is delta G for the decomposition of calcium carbonate at 298 Kelvin and a partial pressure of CO2 at that many bars? Now, what is a bar? A bar is, well, 1 atmosphere of pressure is 1.013 bars. So let's keep on reading. It gives us a reaction. It doesn't give us anything. It wants to solve for it, actually. And it gives us the delta G naught formation for everything. So why don't we just find the delta G naught first, since they give us the knots of the formation? So it would be the products minus reactants for the formations. So CO2 is negative 394 plus, let's see, calcium oxide is negative 604, and we're going to subtract that by the reactants. Our reactants, well, it's just 1 mole of this, and that's negative 1129. And typing that all into your calculator, you get a delta G naught of reaction of 131 kilojoules per mole of reaction. Now, to get from delta G naught to, well, delta G at a new condition, we kind of have to use this equation, which gives us the new condition, delta G, from the old condition, which is at standard state. And we don't have to write the reaction there, kind of overkill, plus R, T, L, and Q. Now, we have some missing variables. We want to know what Q is. Now, Q for this reaction is simply just the pressure of CO2, because everything else is a solid. So let's think about this for a second. How do we find the pressure of CO2? Well, it tells us 0.400 millibars. Let's convert this to bars. So we know that there's 10 to the third bars, well, millibars per bar. So as a consequence, we kind of know that, well, according to this, that 1.013 bar is just 1 atmosphere of pressure. And putting this into your calculator, 0.4 divided by 10 to the 3 divided by 1.013, we get that the pressure of the CO2, according to that, is going to be 3.95 times 10 to the negative 4. And we just plug it in here, and we get that Q is equal to that number, which is a coincidence, but it happens to be true. So now that we know all the values, let's plug it in. Delta G equals delta G naught 131 plus R, since we're dealing with kilojoules, we want to do 8.31 times 10 to the negative 3 times T, which is 298, because they say 298, ln of that. And doing this and typing it into your calculator, you get 131 plus 8.31 times 10 to the negative 3 times 298 times the natural log of the answer that we got from before. And I got delta G is equal to, let's see, do you want to do sig figs? I think we should do that. So, well, actually, I don't think we should. I got 112 kilojoules per mole of reaction, and that's actually just B. So, let's see, what if we wanted to do sig figs? What would we do? So it seems like here there are 3, so we would have 3 decimal places there, and the natural log of 3.95, well, no, the natural log of 3.95 times 10 to the negative 4 is going to be, let's see, let's just rewrite this with 31 plus 8.31 times 10 to the negative 3 times 298 times natural, well, we solved for the natural log, so it should have 3 decimal places since there are 3 digits. So that's actually negative 7.837. And I think when we solve this, what ends up happening is that, well, let's actually just multiply everything together because I really want to do sig figs, and I am not going to stop until I finish. So this is 3 sig figs, since that's 3, that's 3, that's 4, so when you multiply it should be 3, negative 19.4, and it's 0 decimal places, 1 decimal place, so our answer will have no decimal places. So there you go. It seems like the sig figs I did was right. And yeah, that's all for this video actually. Thank you for watching and have a wonderful day everybody.